Go ahead and start recording to this computer.
Okay,
So we are good to go.
we're good to go. Okay, so good afternoon, everybody. I'm the vice president of BAGS and one of the assistant editors for the Leading Edge journal or magazine. And I'm happy to convene this panel on the application of geophysical technology for groundwater management. The topic will be featured in a special issue of the Leading Edge coming in March 2026. And we are actually, for the first time, going to have a group discussion on the topic to be featured in the issue. So I'll take notes here and give a summary of what we found out, right? This is also a first for BAGS. We normally feature a seminar, and we don't normally feature these forums. So it'll be interesting to see how this plays out. I'm joined here by Chris McLennan, a former president of BAGS, and he's graciously agreed to help me manage this thing. And he knows more of the buttons on Zoom than I do. So if it wasn't him sitting here, we'd be fumbling around with these same buttons. So the format of this event is pretty simple. Each panelist will in turn address a single question to start and be given 5 or 10 minutes to answer, including a follow-up question if we need to have one. We'll then open the floor to general questions and discussion. So the makeup of this panel is Dr. Rosemary Knight, a longtime friend. She's a Stanford professor and the lead of the program in the application of geophysical technology for groundwater management in California. Originally from Canada, she still spends a lot of time there. She attended Queen's University in Ontario, completed a PhD at Stanford, and then returned to Canada to teach at UBC. That's where I first met you when you were teaching there. She joined the Stanford faculty in the late 90s, correct? Or is it 2000?
2000.
Okay, and began working on geophysical applications for groundwater soon afterwards. She presently leads the group at Stanford that applies geophysical technology to understand and manage hydrological resources. Reasonable? Okay, good. Okay. Katherine Dlubac is a senior engineering geologist with the California Department of Water Resources. She completed a PhD from Stanford, you might see a pattern here, at 2014 in environmental geophysics. She was Rosemary's student. She worked in consulting for a few years, joined the state of California as an engineering geologist in 2018. Presently, she is the project manager for Department of Water Resources statewide airborne electromagnetic surveys and basin characterization program, and assists in implementing the Sustainable Groundwater Management Act. We'll talk about this in a minute. And incidentally, she's a former BAGS treasurer. Dr. Seogi Kang, my co-editor for the Leading Edge issue, is a professor at the University of Manitoba. He earned his PhD at UBC, was a postdoc and research association in Rosemary's program at Stanford. We're going to run out of Stanford people here pretty quick. So his specialty is data analysis and inversion, and he has considerable experience in interpretation of airborne EM data. Finally, we have Craig Ulrich, not a Stanford guy. He's a researcher at Lawrence Berkeley Lab researcher. He received his MS at Rutgers. He's been in environmental geophysics for his entire career, and he joined LBL in 2011. He has been recently working on applying geophysical technology to groundwater recharge. Okay, so that's our panel here. So we have managers and technical people that will be discussing these issues, right? As a simple preamble, a decade after its passage in 2014, the Sustainable Groundwater Management Act has fundamentally altered California's approach to groundwater. So I'm using this as kind of the basis for a lot of the work that we have been done here to manage the aquifers, right? It mandated the creation of local groundwater sustainability agencies with a plan to achieve sustainability within each agency by 2040. So that means each part of the basin has to be sustainable by 2040 without any funny business. They basically recharge and use their own water. Okay, so that's the fundamental. Now to some questions. We'll start with Rosemary, and I'll pass this to Chris.
All right. I'll also say we have these questions. We have some prepared questions. If there are questions from anyone in the audience, feel free to raise your hand or type them in the chat, and we will either call on you or relay them to our panelists. So Rosemary, the first question we have for you, what technology, geophysical or otherwise, is being applied right now to map and manage groundwater resources? What is it being used for?
Great, thank you. And Mike Welch, you said 10 minutes, not 5 to 10. So I will be between 5 and 10. But I made some notes because it's hard to get through all this in 10 minutes. And one thing no, let me just start. So there are various technologies, various types of sensors and forms of a deployment. And a bit of a definition, I am going to be talking about the technologies that remotely image parts of the subsurface. So using sensors deployed on satellites, aircraft, or through ground-based systems, and now on drones. So I'm going to call all of these Earth imaging technologies because what they deliver images of the subsurface that we interpret and work with to represent the information we want. So okay, Edward's iPhone, please mute. Edward's
Okay,
iPhone.
just a minute.
Who's that? Anyways, okay, so the Earth imaging technology that have been applied in California and around the world, what are you going to use? Well, it really depends on the purpose and the scale. So if my purpose was to better understand an aquifer that I'd identified, size of few football fields, I might move a ground penetrating radar system around. If I was looking for groundwater in Australia, I'd probably want to use an airborne system. So I'll return to this, what you're going to use in terms of your geophysical technology, the purpose and the scale. And I note that in terms of purpose, that originally, or I'd say decades ago, the way geophysical methods were being used was primarily for exploration, looking for groundwater, where very often the interpretation was somewhat qualitative, looking for packages of sand and gravel, looking for the weathered zone lying above the bedrock surface. And it's now increasingly used for management, as was the title of this discussion. And I feel that change from exploration and a more, I'm going to say, qualitative interpretation to getting the information that we really need to inform management decisions has been driven by an improvement in the technology. So an improvement in the technology, the research activities that have allowed us to go from the geophysical data to the information that we really want with a level of confidence that is important for management. And another thing I strongly feel has driven this shift to management is increased partnerships and the awareness that you don't give a job to a geophysicist and they go off and do whatever. There's this close back and forth between the geophysicist and the partners. So the groundwater managers, what do you want? And they say, well, what can you do? Like, what do you want? What can you do? So this partnership, I think, has really been honing our skills as geophysicists to think about how we can use geophysics for management. So I'm now going to focus on the Earth imaging technologies that I feel have seen enthusiastic adoption in California over the last 2 decades. And I have to start with one of those that's on the top or very close to the top of my list. And it's a satellite-based method. So it's INSAR, Interferometric Synthetic Aperture Radar, which is a way of processing SAR data that reveals deformation of the ground surface. Millimeter scale deformation can be picked up. And by the time you've processed and analyzed the data in California, you're mapping out deformation with a spatial resolution on the order of hundreds of meters. But this is really phenomenal that this satellite and the one that's just gone up will revisit points on the ground surface every 6 to 10 days. And so share screen briefly to show the image. This is what the INSAR image looks like over the San Joaquin Valley. And you can see there's regions there that have too many slides open here, up to 2 meters of deformation in the time period 2015 to 2022. So being able to map out, most often we think of satellite remote sensing as giving us information about the surface, but this deformation we see on the surface is actually telling us what's happening in the groundwater system. extracting a large amount of water, the surface is sinking. And we're now working on using this same.
I think you went on mute, Rosemary.
Oh, okay. So, INSAR, what part did you miss? We're now working on recharge. I think I'm clicking too many buttons here. So then moving to ground-based geophysics. So what's been found very useful and to have great value in California and many parts of the world is measuring electrical resistivity. And it contains information about the rock or sediment type, the most resistive things out there being the bedrock. And then as you go to weathered bedrock, less resistive, sands and gravels, less resistive, bring in the clay, less resistive still. So a great way to map out sediments and rock types. It's also very sensitive to salinity. As the amount of salt water goes up, the resistivity goes down. So if you can hold one of those constant, you can map out sediment type or salinity. There's 7 geophysical methods that can be used to map out salinity. Electrical resistivity tomography, I believe, is the method that's been most successfully used around the world, and we've used it in California to look at saltwater intrusion. And that is because the signal doesn't die when it hits the salt water. You can actually image the saltwater wedge. And I will just go to one other picture, which I can't seem to do. Okay, over here. And now share. How many years have I been practicing this? Okay, and here's electrical resistivity tomography along 40 kilometers of Monterey Bay, where we're mapping out in red the saltwater intrusion.
The image isn't showing up, Rosemary.
Yeah, I was gonna say, yeah.
So now you're seeing it?
No, we're not seeing. We see you, but you. Oh,
Okay.
there we go.
Electrical resistivity tomography. The red is where we have salt water all along the California coast, imaging to a depth of about 300 meters. So water managers, am I back? Stopped sharing? Water managers were elated to realize they could get that information. We can also get information about resistivity with electromagnetic methods. Checking my time here. Oh, 3 minutes to go. Frequency or time domain. EM methods also give us electrical resistivity. Ground-based methods have been shown to be useful throughout the world for mapping out changes in sediment type and rock type because of the way that can be related to electrical resistivity. And the great thing about EM methods, because you don't need to hammer electrodes into the ground, they can be deployed with airborne systems, and that is commonly referred to as AEM, the airborne EM systems. Well, here's an example. Here I go again. Of an airborne EM data set that we acquired in the Central Valley in October 2017. And what you see here is the tremendous value of airborne EM in California. Imaging in this location with this system to a depth of 400 meters. The most resistive, the red, we're imaging sands and gravels. The blue is the clay-rich material. And it's talking about airborne EM that really excites me. Stop sharing when we think about how geophysical methods have been used in California. In 2014, as Mike said, the legislature passed the Sustainable Groundwater Management Act. So suddenly everyone had to manage their groundwater. So suddenly everyone cared what was down there. And working with 2 others, talking about purpose and scale, what geophysics do you do? I worked with 2 others and sent a white paper to the governor's office saying, you are not going to get to sustainable groundwater in this state without acquiring data with this airborne EM system. We said you need to acquire 20,000 line kilometers, you need to spend $10 million, it's going to take 2 years. And on the flyer for this panel, I was described as the lead of the groundwater architecture project. Well, that was the 2-year project we ran out of Stanford with fabulous partners, Katherine being one, to figure out how would you do this across the entire state. And what came out of it, I'm sure Katherine's going to talk about, is a huge success, 25,000 kilometers of airborne EM data. Just to wrap up very quickly, the system that was used in California was this helicopter deployed system from Aarhus called SkyTem. Well, the Aarhus team a few years ago came out with a technology that's seeing a lot of use in California, and that is TTEM. So it's a towed system, and you can see this amazing detail down to about 50 meters. Where's the sand and gravel? Where's the clay? And this is being used throughout California to look for locations for recharge. I think that's what I want. Back to your question, what technology? I would say my favorites in California. We can't forget satellite remote sensing, and INSAR is amazing because we can get information below the surface. ERT, airborne EM, and towed EM. With 20 seconds to go.
That's fine. Thank you,
Excellent.
Rosemary.
Thank you.
You answered the question fully and completely. It was a very good answer.
And I didn't chat GPT it.
Exactly. Not yet. That's up to us, right?
So
Use AI.
this is an excellent segue since you've talked so much about how this is being used by California. Katherine, we're gonna jump to you now. How is the state of California using the geophysics, like what Rosemary was talking about, to support groundwater evaluation and sustainable management?
Yeah, great. Thank you. Yeah, and thanks for that intro, Rosemary, to all the work you guys have been doing and all the EM methods, and then briefly hitting on what we're doing in California. So so the California Department of Water Resources has a long history of characterizing groundwater basins in California. We published California's groundwater. It's formerly known as Bulletin 118. We've been publishing that since the 60s, and that provides the up-to-date information on California's groundwater basins. But as Rosemary mentioned, and also as Mike mentioned, in 2014, there was the passing of the Sustainable Groundwater Management Act, or SGMA, and everything changed. And so that is really when people were motivated, as Rosemary mentioned, to characterize their groundwater basins, and there was funding present as well. So where I work at the Department of Water Resources, we really serve two roles under SGMA. We are the regulatory agency, so we review the groundwater basin's progress towards sustainability, and we're also the technical supporting agency. So we provide technical support to groundwater sustainability agencies to help them achieve their goals. And so, as Rosemary mentioned, there was the pilot studies in 2018 to 2020, and that helped to lay this pathway out for us to understand how we could use airborne electromagnetic surveys to support groundwater basins and understanding what their groundwater infrastructure looked like. And then, as Rosemary also mentioned, there was a white paper that Rosemary and two others submitted to our governor, and the Department of Water Resources received this $12 million to go out and collect these airborne electromagnetic surveys across the state. So I'm going to jump into a slide quickly just to show you what we did and the data we collected. So just give me a second here. I will share. Okay. So as a part.
So it's contagious. We can't see your screen. Up there. Got it.
Do you see it? Okay. Okay. Wonderful. Right. So in 2020 we started this, in 2021 we started this statewide airborne electromagnetic surveying project, where we collected about 26,000 line kilometers of AEM data across the state. As a part of that data collection, we oriented flight lines so that we were capturing heterogeneity within groundwater basins. We collected this reconnaissance type data. So there was a coarse grit spacing. You can see the flight lines here. And we, at the department, we did not process and invert the data ourselves. We worked with a consulting firm who did the geophysical data processing, inversion, and interpretation. And so as a part of this project, we had all of the data that we collected interpreted for texture. So interpreted for the percent coarseness or the percent fine within the aquifer itself. So as a part of doing that, we also digitized a lot of data. So I think 16,000, oh, that's 16,000 there, but thousands of well completion reports and thousands of geophysical logs were all digitized to support us in this interpretation of the airborne electromagnetic data that we collected for texture, right? So the idea here was that we wanted to make sure that the data we collected were going to be usable by groundwater managers, by consultants, and that really to try to, just to try to show that the data would be useful and to help folks use it. So we collected all of this data. We made it all publicly available nearly as soon as we received it. So there was about a 6-month turnaround from data collection to data publication. So we published everything on the California Natural Resource Agency Open Data Portal for folks to download. And so that included the raw data sets if professional geophysicists wanted to reinterpret the data, or also these inverted products and the interpreted products. So everything was made publicly available. And then we also went to great lengths to ensure that the public could access and view the data. So geophysical data, I think, as we all know as geophysicists, unless you have geophysical software where you can see this data, where you can work with it, it's very difficult to see or use, or to know really what's happening with this geophysical measurement that you're collecting under the earth. So we went to great lengths to ensure that the data were publicly available. So we have data that are viewable in map form. So this is our Sigma data viewer. And then we have several types of other data visualization software or platforms, that are accessible online. And so this is something that can show the user what that profile of AEM data looks like in the subsurface, both the electrical resistivity and the coarse fraction, and then where they are on the surface. So basically where you're standing, what it looks like beneath your feet. So we did lots and lots to collect the data and get data publicly accessible to folks. But we also wanted to make sure that the data were usable by consultants and by practitioners and local groundwater managers. So what we wanted to do was develop tools and develop outputs so the products could be used. So after the completion of our statewide airborne electromagnetic surveys, we launched our basin characterization program, where really the focus of this program has 3 tiers. It's to collect data, to interpret data, and then to provide outputs that are really decision support tools for groundwater managers. So to help them understand how to handle various components to change groundwater sustainability. So things like where to put water to conduct groundwater recharge, where to put water in the ground to mitigate subsidence, the subsidence that Rosemary mentioned, and various components like that. So as a part then of basin characterization, actually before we even launched this program, several years before that, we had our teams had some of our consultant teams start to work on using the airborne electromagnetic data, putting them into tools so that they could be used to create things like texture models or aquifer flow parameters, so they could go into groundwater flow models or stratigraphy or various components. So we have a set of tools that the teams developed, and those tools take in that airborne electromagnetic data interpreted for lithology or for texture. They take in groundwater lithology, groundwater levels, geologic interpretations. You can put them into these various tool sets and get aquifer flow parameters, texture model, stratigraphy. We also then have the texture model component. So this texture model is actually really a powerful model that contains a lot of information. It describes in your voxelized space what percent fine or what percent coarse the materials are. And you can imagine that can help you to understand where the clays are within your aquifer, where the sands are, and where various flow pathways are. So we use that texture model. We then integrate soil conditions, depth to groundwater, and then integrate that into an aquifer recharge potential analysis to develop aquifer recharge potential maps. So these are then a series of maps that help groundwater managers better understand what the potential is to put water into the ground, right? So there's some areas within their basin that may be dominated by fine materials where groundwater infiltration will occur more slowly, and some areas that are dominated by coarse grain materials that might have pathways even down to the deeper portion of the aquifer. And so they might want to prioritize conducting recharge at those locations. Then now, as a next component to this, so developing these aquifer recharge potential maps, we're now going in, working with the local groundwater managers, going into these sites that have higher recharge potential, that have landowners that are interested in conducting recharge, and going in and collecting this towed electromagnetic data. So the one that Rosemary mentioned just at the end there. So collecting that towed EM data at their sites to see with higher resolution if there are finer grain units beneath the parcel. And then also looking at using this flow temp system. So it's the same electromagnetic system now towed behind a boat, because one of the other components that we're interested in supporting local groundwater managers and characterizing is surface water depletions that may occur if you're pumping groundwater, but it's actually coming from the surface water system. So there's a component there of supporting agencies and understanding what's beneath that riverbed system. So we see our role supporting GSAs in helping them to, one, use this geophysical data, and then also, there's the economy of scale of collecting all of this data by one entity, by having us do all of the data processing, interpretation, getting it out there. Again, this was only about $12 million for all of the data that we collected throughout the state. And then we're also going out and collecting new types of data. So the FlowTem, we collected FlowTem in the state a few months back just to see what could we see with this FlowTem type instrument. We're also working to potentially go and collect drone EM data or EM data collected with a small helicopter, but basically various types of data. So helping local agencies better understand what methods are out there and exist that could support their needs and help them better understand their aquifer system to support their groundwater management activities. Yeah, so I think that's really what we're doing here at the state, is helping folks to, one, collect the data, use the data, and then go out and collect more data wherever needed to help folks better understand what their groundwater systems look like.
I have one brief question before we move to the next speaker. How well is this absorbed? How well do the growers and agencies understand this? Is there a big education process?
The airborne electromagnetic data, or the towed EM data, or everything?
Basically, the output, the map you give them, and how are they using it?
Well, right. So so there's a series. So there are a few levels there. So one is connecting with consultants. Of course, that's easier because these are basically technical experts. Connecting with groundwater managers is another level. And so because we're at the Department of Water Resources, we do connect with groundwater managers through various channels. So it is important for us to make these products as simple as possible. So I mentioned that we have the Sigma data viewer. That's a map view. That's something that we've had out for a long time. It contains groundwater levels. It's an interface that people are familiar with and know how to use. So that one is fairly straightforward, and we put all of our mapped and modeled products there. And then for more technical users, we have that platform that I showed you where you can see the subsurface and you can see where you are in a map view and then see where you are in the subsurface. That is for a more technical user, but it takes quite a few conversations to connect with groundwater managers and with growers. I had a meeting last week with growers talking to them about what TOTEM could provide for them, what information we had from these aquifer recharge potential maps, why we wanted to help them with the TOTEM data. And it's really, I think, also, as Rosemary mentioned, making not only these connections between the geophysicist and the geologist or the hydrogeologist and the groundwater manager, but then also the locals, right? So making sure that you can make all these connections and talk to all these people. And because of Sigma, folks are becoming more aware that groundwater exists under their feet, and that geophysics is a thing. So I'll say also, just lastly, that as a part of the statewide surveys, we mailed letters out to all parcel owners who were within a 3-mile buffer of these flight lines that we flew. So we mailed out over 200,000 letters to folks in California, telling them about geophysics, essentially, showing them a picture of the airborne system and telling them about geophysics and that this method exists and that we were going to collect data in their area. So that was, I think, a huge public campaign of saying this is a methodology that's out there and can be used. And so, yeah, I think that was pretty successful, and we're getting good participation of folks using the data and wanting to collect data on their parcels.
Thank you, Katherine.
Great, thank you. So we're next going to go over to Craig. And Katherine, you talked about creating aquifer recharge potentials. So this is a great pivot to Craig. What technologies do you see are being used to understand and control the man-made recharge in these areas? And can we use these to estimate natural recharge?
Yeah, so can you guys hear me?
Yes.
Yeah, we can.
All right, excellent. Thank you. Well, thanks. First off, thanks for having me join the panel. This is wonderful, and a lot of great discussions so far and lead in for me. So what I'm basically going to talk about is, sort of kind of extending on what Rosemary and Katherine were talking about, which is, sort of quantifying the subsurface and understanding it, but also quantifying recharge. And I really like what Katherine, what you were saying there at the end about reaching out to farmers, right? And letting them know that this technology is available. It can provide useful information for them, et cetera, et cetera. Please be part of this movement of trying to put more water in the ground. And, that's not like lost on us, right? Because even a lot of folks, even in the like geotechnical side that are building, sort of BMPs inside urban areas to do recharge, they also don't know about a lot of the geophysical methods and what the geophysical methods can provide them. A lot, some one of the projects I'm part of, they were planning to come out and do CPTs after every rain event, for instance, right? And while that's a way of getting at changes in moisture content, it's also going to compromise the BMP that you built because you're going to poke a lot of holes in it. So maybe it recharges better that way. I don't know, but anyway, I think it's really useful to think about and spread the word. So Katherine, I'm glad you mentioned that, because I think that's a really important thing that we all need to do, and I think that's the benefit of the BAG seminars. So let me share, if I can also share with being successful.
Quick question, Craig. You mentioned BMPs. What does that stand
Oh
for?
yeah, sorry. It's a BMP is what's called a best management practice, which doesn't make sense, but it's actually a description for infrastructure like bioswales, dry wells, infiltration galleries, et cetera, that are used to convey water into the ground for doing managed aquifer recharge in small scale areas like urban settings, or what I like to call urban MAR, right? We have ag MAR, we have urban MAR, we have all types of MAR. So, and we're doing the same thing at the small scale too, just like Rosemary hinted at, is basically finding these fast paths, right? And the fast paths that are key to making sure we can get water in the ground. The sort of technologies, that I think are important to use and to quantify recharge that we're using is, a whole array of your traditional sensors, like you're still using pressure transducers and monitoring wells, to monitor groundwater levels and how they rebound. But you're also integrating geophysics into that and doing this sort of multi-method approach to understanding and quantifying recharge. Some of the technologies we're using are thermal sensors. A lot. You can also think about it as distributed temperature sensing if you're using fiber. But these are vertical sensors of temperature strings that just monitor the temperature flux into the ground, which we can then use that to convert to like infiltration rates. We're talking borehole logging, some neutron probes and sensors, a lot of soil moisture sensors coupled with soil cores to really look at optimizing recharge. And that's what I focus on. And you can, don't need to talk about the electromagnetics because Rosemary covered that very well. But here's what some of the stuff we've been working on it with like Metropolitan Water is ways to understand their infiltration at their basins and quantify these basins, because a lot of information is not known about the basin other than maybe if they used like a yardstick to measure infiltration rates and they have a single infiltration rate for a basin. But the opportunity here is to use these high resolution geophysical methods to better understand and quantify those spatial infiltration rates, right? So for instance, we see different ponds up here on the top left that have sands, and we have these small, quick infiltration paths, and then the rest of the pond catches up. And we see most of the flow down through one side of the basin. But overall, this puts on like about 1.5 acre feet per day with around 2 to 3 feet of standing water. Contrast that to the pond next to it, and keep in mind there's 30 ponds like at this facility. We have only about just under a half acre of recharge, half acre foot of recharge per day in this pond, just due to the simple fact that we have a little bit of overburdened soils that are silty, maybe silty clayey. And so they didn't understand that existed. When you walk around in these basins, it looks like it's all the same type of soil, but it's actually not. And so we see that this stuff, we can use the geophysics to derive these subsurface images that provide information about how these basins are likely going to perform. And then we can do these pilot experiments and put water on to understand and quantify how much water is actually going into the subsurface and how deep it's going, because that's another type of information that water agencies want to know, because it determines what sort of credit they get from DWR for the technology that they're using to convey water into the subsurface to meet Sigma requirements. Again, I should mention that we use mainly electrical resistivity, because as was mentioned earlier, Rosemary, it's one of the best performing systems for monitoring changes in water content when everything else is held equal. So we don't see really changes we know the conductivity of the water that we're putting in, and we know the soils don't change. So our changes that we're seeing is just due to soil moisture infiltration. So from these two studies that you see here on the top and on the left, and this was an Agmar field on the left where we highlighted, it was a field that was listed in the SAGB index, which is an early index that gets at like where there's good places to do infiltration and where there's necessarily not the best places to do infiltration. And this field was designated with a moderately poor potential. But we actually found in the one field where we were going to do some flooding that we actually had these sand lenses that come up near the surface, and they pretty much conveyed almost all the water into the subsurface. Now, this is really insightful information for a farmer, because if they're worried about not wanting to inundate the full field, they could think about rerouting their berms to focus at these locations of high infiltration soils versus low permeability soils. And from this, we ended up getting some interest and said, well, can we work on BMPs? Like, this is a dry well system sitting here, right? And it's under a parking lot. It's pre-existing, but they don't understand how it functions in the long term. So actually putting in boreholes and doing crosswell surveys with ERT, because EM systems aren't going to be usable in this area due to cultural noise, we can actually get at and quantify how much recharge is happening and help them understand basically the flow of fluids in the subsurface as they exit this BMP. And why is that important? Well, just them visually seeing how water is moving without having to put in a bunch of sentinel wells around the system. They can better understand where it's going, but they can also then use this to make decisions, and which is what they're actually going to do just from this initial pilot study, is they're going to add more dry wells in and put more and divert more stormwater capture into these systems to put more water in the ground in the LA basin. And so just visually, this helps, right? The geophysics can help just by seeing what's going on, let alone just to quantify this recharge. But that's the next step, is to actually quantify this recharge. And there we've used a number of different models. Sometimes we're using, like I mentioned, the thermal sensing to estimate recharge rates, or we use EM data to estimate recharge rates with a Hydros 1D model, and we use and transform it into, we transform the EM data through a fit with hydraulic conductivity to estimate the recharge rates in each pond. And then we can do more complex, right? This is the beauty of the geophysical data and how rich it is that we can then even move that into a 3D hydrogeologic model and look at in 3D and really capture high resolution recharge rates and estimate recharge volumes per pond or per basin. Or you can think about, when scaling this, we can then move it around with inside a large spreading ground and just better understand what recharge is going on with inside, let's say, a larger 100-acre, 200-acre spreading ground, right? This can be really important for water agencies and purveyors to know what their recharge rates are, because, and then low-hanging fruit is, can we then modify these potential basins to increase their recharge at these ponds, right? To improve our water recharge capacity. And I would say that's, I don't know where I'm at on time. Let me stop sharing for a second. That is what we are finding to be like the really useful technologies for capturing recharge in urban settings, and then also using that to scale outside. One I was going to bring up, but Rosemary already hit on it, so I don't need to do it, is then scaling from, what your need is, right? Going from a site area, but like LA Basin on a whole can put they have hundreds of these around. But then again, you want to know, well, what effect is this having in the basin? And then you can go to doing satellite monitoring for the basin scale, right? So I think that geophysical tools like Katherine and Rosemary talked about is we have these series of tools that can actually characterize the subsurface from site scales all the way up to basin scale, and we can monitor with them. And I think that's it's really exciting.
Are they using these now? Are they using this, for example, if you have a wet year, do they find out how much natural recharge has been going into the ground versus flowing out to the sea?
Yeah, so I would say that the state, and Katherine can jump in here and probably tell me I'm wrong or right or half right on this, because let me go down. Sorry. What I kind of put a little table together, and these systems work really well for, and sorry, I'm trying to find the share button again. There we go. Can you guys see that?
Not yet. There we are.
You can see it?
Yeah.
So yeah, you kind of led into this next question, which was how much is being, recharged naturally versus, let's say, man-made, or what we call managed aquifer recharge, which is just us assisting Mother Nature. California is generally a 60-40 split on water years, right? We typically use 60% of surface water allocation, and then 40% subsurface on groundwater extraction. That's on an average year. And then of course, if it's a drier year, it shifts one way, and if we have a wet year, then it may shift the other way, and we can rely more on surface water. I put in here New Mexico because I was just down in New Mexico giving a talk on this technologies. And they're a 50-50 split. And I think because when you look at the changing snowpack distribution, right? Snowpack is becoming less. It's also snowpack is melting earlier, but not only earlier, it's also shifting where it falls. So our sort of historical models are sort of breaking down a little bit, right? That's discussions I've been having with different groups, is that it's harder to predict where we're going to have snow and how much. So, and you can see from the bottom right that we have groundwater drought issues everywhere across the US almost. So it's something that's not unique to California. And going back to this, what we're putting in versus what we're, extracting, we're still under recharging by quite a bit. I mean, we do put in something like 4 million acre feet, 2 to 4 million acre feet per year, depending on the water year, is what we can recharge. But we're also taking out a lot more still too. So, I think my personal opinion is that we do need to build more sites based on the airborne EM data, get as many sites ready as we can. And can we use this technology to do that? Yeah, for sure. Monitoring natural recharge, that's a little harder because I think that's a little harder. Maybe the panel can jump way up on their opinion on here, but that's usually just lakes and rivers, right? Like that's the natural recharge, because we don't really have much over floodplain flow, right? Is because we channelize a lot of things. So, but I will say one of the I don't know if anybody knew this, but like through aggressive investment, Santa Monica is really interesting because they're going to be probably 80. Their goal was to be 95 to 100% off imported water by 2030, but they've had some delays on some projects. So they expect to be 85% off of imported water by 2030. And that's through these type of things we're discussing here, really characterizing the subsurface, underestimating like where it's going to be the best place to put water in the ground, and then building the infrastructure to do it.
Great. Thank you, Craig. It's very useful.
Yeah. So last, certainly not least, we're going to come to Seogi. The first three speakers have all mentioned kind of how important it is to be able to relate the data that we get with the physical characteristics of the Earth. And so what methods or combination of methods do you find available to define this aquifer environment? And do you see a role for AI or machine learning in the data processing and inversion steps?
Yeah, first, thanks for this amazing event. And when I was actually thinking about aquifer environment, I felt that's a very tough to define. And I think that's sort of how I generally learn throughout like working on various types of geophysical data, participating like a groundwater architecture project and a whole bunch of other projects, trying to utilize the geophysical data in a way that can answer important questions related to groundwater. We were able to sort of say something about some part of the problem we may say we would address, but the overall, what I felt in general, it's very hard to kind of address those questions. Like, let's say, if you're thinking about aquifer and like environment, if that's the water storage, it's very hard to tell. Just utilizing geophysics to tell, okay, we have X amount of water that we can utilize. So I think that's the general problem. And so obviously, as you sort of your question kind of inferred, we need to bringing in other data set like a driller's log or head level data or satellite data or multiple types of geophysical data, because geophysical data have a different scales on it. So at a certain point, like, and then at the end, like we cannot really, without using the process-based model, it's hard to kind of estimate what would happen in the context of water storage, water quality. So at the end of the day, we really need to bring in all the information, integrate it in a way that can answer those questions. So I think that's the sort of a high level big challenge, I guess. So I think that's, I don't know the answer. And then I think your second question, AI can play a role, probably. So I'm gonna, that's sort of the high level point. I prepared a couple of slides so that I can work through. So I'm gonna a bit more focus on my expertise, electromagnetic geophysics, and what it could bring in. And then at the end, I'll probably answer some of those AI related questions. Yeah, that was the question. So I'm an electromagnetic geophysicist. So to me, at a high level, there are various types of geophysics. But what we're doing, we're injecting some sort of energy and then have some interaction at the subsurface. We're seeing what we're sensing is not the hydrogeology, it's the electrical resistivity, right? And then we're getting some data at the surface, or it could use airborne, ground, whatever types of sensors. Then there are many types of geophysical methods. I think that sometimes it's quite important to recognize, because using a relevant methodology, let's say we're working on really large scale, we might be able to use some airborne, but let's say if we're working on a local recharge site, this may not be a right tool. So you may want to either use an ERT or TODM types of system. Or if you want to see deeper, like you're really interested in like a deeper bedrock, you may want to more passive style of electromagnetic method called magnetotorics. So, but high level, it's important to recognize there are methodologies. Depending upon what you're trying to image, you need to choose a right methodology. And once you collect the data, that's your starting point. This is an airborne example. What we are doing, like that doesn't really give us a resistivity. So what we do, we invert those data and we try to find three-dimensional model that can fit the data. And what we really need to remember here, like geophysics is sensitive to the large scale features. So we can miss the small scale features like 1 meter thick clay at 100-meter depth. We may not have a chance to image using an airborne EM, for instance. And also, what we need to remember is we need to prove, like what we're getting is not a direct information about hydrogeology. We're getting an indirect information about resistivity. So it's critical to relate the resistivity with some sort of hydrogeology. So you probably need to bring in additional data set. So speaking of the scale, this is slightly the same data set that Katherine have shown, but put it in a slightly different three-dimensional view. So we can actually use the airborne EM at a regional scale, like a Central Valley scale. It's about 700-kilometer length scale. And we can also use the basin scale. This is like we're moving into Korea. Rosemary have shown some of the Tulare data. I think it's somewhere here. And so we can also use the same data at a sub-basin scale, like 60 by 60 kilometer-ish scale. And if we're going into a local recharge site, say 100 meter, 800 meter by 800 meter, then we need to use a slightly different model. Rather than airborne EM, we may better use a TODM or an ERT types of method because we need a higher resolution. So it's important that we have a multiple methodology that can give us a multiple resolution about electrical resistivity images of the subsurface. Then, as I said, what we're sensing is the resistivity, but hydrogeologists, it may not be an interest. So we really need to kind of find the connection between resistivity and sort of what the aquifer parameters. Let's say in Central Valley, we're working on a sedimentary aquifer system. So what we care is, okay, how much fine-grained information, materials we have, how much coarse-grained materials we have. So if we have some sort of driller's law that give us information about those sediment type, then we can build the relationship between resistivity and sediment type and potentially transform resistivity into something like a percent coarse. Then that could be a useful product. Again, that's the limitation of geophysics, because what we're sensing is the resistivity, but what other people want is more of a hydrogeology. And this was I thought like an interesting example. So this is the same data set, and blue-red is how much coarse-grained materials you have. And if I pick a location here, this is in between the airborne EM lines. So we don't have the data. So if I interpolate, and that area is like highly, a lot of coarse-grained materials is located. But if you actually go out and do the survey and create a similar how much coarse-grained materials we have, we see a lot of changes. And actually, that's the part of what Katherine mentioned. They go out again with the high resolution data, and you can find more fine-grained structures, which could be quite important in the context of your problems. So we need to choose the right methodology. That was sort of about the first question. And the second question, do you see a role for AI? Yes, obviously. I think the reason why I said obviously, what I'm seeing is a trend. There's an emerging, increasing sort of amount of airborne EM data collected throughout the global scale. So Central Valley was one example about the statewide, but if you go to Australia, they're collecting continent-wide. And even in US, there was data collected in Kansas, and New Mexico is actually just started collecting the data in the context of groundwater problems. So there's a need to, we need to rapidly process invert and in a way that can have some sort of three-dimensional resistivity model that people can interpret. So I see a really interesting kind of sort of a floor that AI can play a role. Because if you think about where AI can actually work, means like we need a lot of data. So we're getting a lot of data. So it's a matter of how are we going to implement that and then turn that into a useful product. So the first place that I am seeing is an automated processing scheme. So collecting the data, we need to actually process and invert. It's not a small amount of work, but there are a lot of pieces that we can really automate. So for instance, like to invert, if I want to invert data, I need high quality data. So we need to remove the noise and filter out. And also I need some estimate about how much errors we have. And that's an input of an inversion. It took a while to get there. So if we can automate that process and we can reduce the cost, we can save the time potentially, so we can actually potentially increase the amount of data that you can collect with the same budget, for instance. So I think that this is an obvious place, and other areas, like for instance, seismology, this has been done. So I see that there's more kind of emerging techniques in our area as well. And second one is, I think it's more, much more challenging. So at the end of the day, as I said, what we want to integrate all this information and turn that into a useful product. And one potential way is bringing in all this geophysical data, in situ data, into some sort of like a process-based modeling. For instance, groundwater modeling for aquifer environment. And I think there are a lot of trials, but we haven't got there, and there's still a lot of challenges. But I read a couple of articles in seismic and medical imaging. They are much more advanced, and I saw some sort of useful or like kind of potential in there. So hopefully we can sort of adopt those kind of things, and I hope that AI can play a big role. But I think that there are a lot to go, a lot of way to go. Thank you.
Thank you, Seogi.
Thank you.
Can I ask a quick question? A little bit more detail on that. AI is a very broad and kind of buzzwordy thing. Is there a specific kind of AI process or machine learning process that you would see more useful? Like, I'm assuming we're not talking large language models here, but you know, the conventional AI when people think of that. But what kind of machine learning methods would you be leaning towards for this?
I think that for processing, I guess I think that you can use very traditional neural nets even, and that could actually work quite well. So that one, I think it's more sort of straightforward. But for the second one, I think that's where a lot of research is actually coming in. And one of the latest research that I've seen was like using this diffusion model and to kind of sort of replace, I'm not sure that's the right word, about the inversion process, and further to find, and rather than finding one model, many models. So I think there for some example, like doing it for an image processing. Let's say you remove a part of the images and you can replicate those images, and with many of them, and using those diffusion models. So I see kind of a big potential there, but there are probably lots of other architecture that I don't know, because it's every day they're developing new things.
Yeah.
Could you walk us through the workflow, just in general terms? They collect the data with airborne EM, and now you get these transients. Really, that's all you get. You get a whole bunch of transients. How do you go from there to your 3D resistivity model?
So there are a couple of processes. Like so, for a very in a simple manner, acquisition company collect the data. They give you a raw data with many sampling points. Then you stack over a certain interval, let's say 30-40 meter interval along a flight line. So in a simple sense, what you can do a simple stacking. Then that gives you errors, like a standard deviation of data. So that's the minimal level of error estimation that you can do. Then what you do, like there's typical noise that you know. For instance, like if you're flying over power lines, there's specific sort of a shape that you can find, and then you lay over with the map, and you can manually sort of remove that. One like a potential area, right, that you can definitely try machine learning to remove that. So then you have this you remove it, and you have some high quality data because you remove those noisy parts, and then you may have some estimate of error, but that's not the end. That's not the true error. So you within the inversion process, you need to kind of further estimate that, and that's a part of the problem, and that's kind of challenging.
So you start with a 1D distribution, or is it always 3D? And then how many of these stacks
Oh,
together?
I think for this hydrogeologic cases, typical tool is a 1D inversion. 3D inversion, I think I haven't seen many, very few cases which have been used. So what you do use 1D inversion, but in a way that you're not really doing one by one. You invert everything together with some constraint. For instance, like resistivity values in vertical and lateral dimension, even between the lines, are somewhat smooth. So that's a typical constraint that you're putting in.
Okay, great. So, all right, thank you. Great. We've had some very nice background. I'd like to open this up to the floor, to anyone who's online here that has a question for any of these panelists or any further discussion. Please speak up, unmute, and give us your mind.
Hey, Mike, this is David.
Yeah.
I have a comment on Seogi's last bit of comments, because the 1D nature of these inversions does sometimes worry me a little bit in terms of overinterpretation of resistivity changes along a line and that sort of thing, even if you put the constraints in and whatnot. And one of the things I think we're at LBL we're starting to look at, or I'm starting to look at, and hopefully going to work with Craig and Yu-Shin on, is because modern acquisition systems, they're not, we used to collect airborne time domain data a certain way in the past, where we only, because of data storage limitations and whatnot, where we'd average and just only store the decay curve, right? We wouldn't, but now modern systems, they sample at a high rate and they can store the whole waveform. And so that opens up the possibility of Fourier transforming and doing the 3D inversions in the frequency domain, which are much more tractable than doing a 3D time domain inversion. And so I'm going to start looking at this. It seems like, at least for localized inversion, where it's not, you look at the 1D inversion results and it's not just continuous across the section very smoothly, but there are some of these stripes that appear and whatnot, or weird things. I think it might open up a lot of possibilities. The other thing that I wanted to mention about acquisition, another research topic that isn't that much more expensive than the airborne acquisition, because you're still doing airborne or drone acquisition, is using a grounded source during the acquisition, because that gives you a different sensitivity to the subsurface, because you have vertical currents then in the subsurface, which are going to be way more sensitive to resistive layers at depth than the airborne EM. And so that's always one of the problems with airborne EM and MT and the inductive methods, is you can't really find a sharp boundary for the base of the conductor unless you really have some good constraints. It always just really smears through it. But once you add a grounded source and you get vertical currents going into the subsurface, then you become much more sensitive to those boundaries and being able to resolve them. So just a couple of comments I wanted to put in there.
Okay, great. So technology is in process, right? So one of the things I would be interested in is that when we did a lot of the crosswell work, we got a lot of information on the residuals. In other words, when you collect the data and you fit it to a 1D inversion, it doesn't fit perfectly. There's some parts that don't fit. And if you look at this as part of a basin, they may form a pattern. Have we ever done that?
General
Seogi, are you still?
Yeah, Seogi or Rosemary, if you want to respond to any of this.
Mike, can you repeat your question one more time?
So you're fitting the data to a 1D model, right?
Mm-hmm.
especially if you look basin where there's many waveforms fitting to a 1D model, and there will be a misfit. Doesn't fit perfectly because it's not really a 1D Earth. Are you looking at that misfit function either sounding by sounding or as a whole series of models? And if so, does it tell you anything?
Yeah, I usually do, but usually that doesn't tell me much because even if you have a pretty strong 3D effect, we can still fit with the 1D. So fitting is not a big deal. So I think because using that data fit, the 1D model, as an indicator of whether there's a 3D artifacts coming in, I think that doesn't work. So we usually try to overfit, like kind of fit as much as we can. And then you look at the images and see there's a weird structure. If that's because they're a typical sort of three-dimensional structure, then you kind of remove those portion of the data. Or if you have a 3D simulation code, you can test that out, but that rarely happens.
I remember years and years ago, my own PhD thesis, right, was on transient EM, the central loop, which is really an analogy to this airborne EM system. At some time, you're inducing current to flow in the ground, and then that current will hit, if it hits a barrier, you'll see it from some distance away. So that's where I'm thinking the residual, especially if you're in conductive area, will show you the resistor some distance away, quite a bit ways away from the data itself, and that would pile up pretty easily.
Mike, can I put a question out there?
Please.
To fellow panelists, and I really want to tap into the collective wisdom in this room. David Allenbaugh, you might have a solution. So as I started off saying, electrical resistivity is so useful. We can map out sediment type, we could map out salinity, but unfortunately there's always that ambiguity. And what we're starting to find with some of the airborne EM data is there are parts of the valley where it looks very low resistivity. It's because it's high salinity. And now we're finding in our TTEM data, even though it looks low resistivity, it's because it's saline. So you have to go in on an even finer scale to figure out whether you're looking at clay or salt water. Now, Seogi, I was super enthusiastic way back for you looking at the IP effect in the airborne EM. Like if we had an airborne IP that really worked, but the signal wasn't strong enough for you to be able to get the IP, if we had a way of doing seismic, which would tell us that it was clay, and is there some way of dealing with this saltwater clay ambiguity?
I saw someone had a picture of passive seismic optical. Is anybody actually doing stuff? Who was it who had the picture in their slides?
Well, Craig, you were talking about some fiber sensing. Are you? Anyway, Seogi, can we get IP from airborne?
I've got an idea here, and Seogi could probably answer this better than I can. But I'm just wondering, as Mike mentioned, typically these systems measure vertical components only of the. But what if we started measuring 3 components? Now the horizontal components are more sensitive to, I'm just thinking as I'm talking here and realizing it's, at least with the totem, you might be able to rig something up to measure horizontal components off the system that might have more IP information. As I don't know. I haven't done any of the modeling.
Okay,
but
so this is everyone's assignment due in 2 weeks. Please email me your answers.
or that's where I like this grounded source with a drone, or collecting the data.
Well, we did that actually over in Tulare. Seogi looked at, with where we had the source went completely around the almond grove and the receiver flew up and down between the trees. Yeah, so maybe that is, ERT comes, we've got a vertical current. So even by combining ERT and
ERT, if you have the time and effort to put into it, but it is so much more effort intensive.
Yeah.
Whereas if you just put out a couple grounded sources that are in different polarizations and then do that same thing that you're talking, instead of a large loop, that's where I'm thinking you might be able to get the IP information from the measurements.
So years and years ago, one of the things I looked at in this was looking at the horizontal spatial derivative of the field. because that will tell you something far away, often at later times. For example, if you have a large derivative at late times, that means there's a barrier some distance away, right? And early times, the barrier is close. So that's something that we could do. It's kind of low fruit. It's pretty easy to do it with the data you have, just looking at the derivative. A, it will give you a lot more confidence in your 1D model. And B, it'll let you know if something's coming. And if there's a lateral change coming. And I think with Rosemary's questions, a lot of these are related. The salinity variation also relates to the texture variation. Basically, that there's these locally, there's places where the water cannot drain, so it gets saltier and saltier.
No, Mike, a lot of it's ag runoff. A lot of it's in the Central Valley, years of fertilizer application, it's nitrate loading.
Can't drain. Yeah.
Yeah.
I mean, that's a very important thing. And why would you expect a big IP clays will give you a bigger IP.
Well, that's what we're looking for. To know that for sure this low resistivity is clay, we would want an IP effect. Otherwise, it might be salt water. So it's to remove the ambiguity between saline and clay.
Earlier on, there was a geophysical paper by Gerald Holman, who looked at a transient EM. He was looking at the Cyrotem system. I don't know if this translates to that. And he could see IP effects when they ran Cyrotem over clay bodies, right? Which is not that dissimilar from the EM. So there might be IP effects in your data already.
Oh, I'm sure there are. It's a matter of finding them. Kevin's had his hand up for quite a while.
Go to Kevin for a second.
Yes.
Yeah, so great talk for everyone. I suspect that if you could put a few seismometers out, you could probably back out, whether an anomaly is due to some sort of fluid infiltration rather than just, being very salty or due to clay. I think that the problem with using ambient noise tomography or something is that you need your sensors deployed out for a few days, if not a little bit more, in order to get enough correlation stacks to make a good tomographic model. That being said, I'm not an expert in ambient noise. I just did it a little bit in Utah, so take it with a grain of salt. But I had a question in general for more of the panelists about the distribution of when you're making these inverse models. How much, what is the proportion of these inverse methods that are like a Monte Carlo kind of forward model evaluation versus traditional inversion? And is there a preference across different methods or different?
Seogi.
Yes.
Yeah, I think for instance, what DWR provided, it's all gradient-based inversion. There's non-Monte Carlo or stochastic types of inversion. And one of the reasons, actually, you have zillions of data, and doing Markov chain Monte Carlo for each sounding, still quite challenging with the existing computing power. So, and that's the main but my general feeling using Markov chain Monte Carlo, if you are really not setting up your priors and things correctly, kind of trying to find simply trying to define undefined a high level uncertainty, it's almost impossible, because each pixel or uncertainty in the subsurface about the geophysical data is infinite. So if you're going in that route, you need to really define a specific kind of question in the context of you're trying to measure the uncertainty. So what's traditionally and what's typically done is using the gradient-based inversion for one data.
I have a very general question about the leading edge, folks.
Can I just respond to the ambient noise tomography? Because Kevin, yeah, you need to leave it out a long time. We have just deployed 6 seismometers. We have 8 more to go in the Kuya subbasin, and we're leaving them out for 3 years. We're also leasing a stretch of fiber, and we will be doing continuous monitoring for 3 years. So I am super excited to see what we can see at that scale of imaging with ambient noise.
Hey, I wanted to mention real quick to Seogi's point about Bayesian inversion, and my screen froze up, so I couldn't say it right after he got done talking. Ananda Gray at CSIRO down in Australia, he's come up with a 1D Bayesian constrained inversion, and he has been. It's quick enough that he has done all of the airborne EM data across the continent of Australia, which is like 50% of all the publicly available that they've used for groundwater characterization and whatnot in Australia. So there has been quite a bit of progress made on that front by him, at least. So just wanted to bring that up.
Safe.
So my question was about what is the outcome you want from publishing this in Leading Edge? Like, you've got a bunch of mostly geophysicists who are going to read it. Is it? I've got three options for you. One is you get more funding for EM research, for groundwater research. Another is everybody says great story, but or you recruit students. But is there like, what is it you want them to do? Other than say, great, I never knew that, there was such cute data. Is there a thing you want done, and does that change the way you present it in the Leading Edge if there's a thing you want done?
Well, mainly we're capturing the energy here. We're capturing the effort and what people are, what is the vision, if we can. Rosemary's vision on this, which is very useful, and how it's being done, and then what are we getting out of it? So it's not, we're not asking people for a specific thing. We're trying to capture what they're doing already.
And Dave, what I'm writing in the Leading Edge is more of a story. I've given this talk a couple times recently about how did this happen? And it's what I'm constantly now telling students. If you have an idea and you think this is the way it should be done, go political. And I think as geoscientists, we just love the research we're doing, and you can spend 24 hours a day doing your research, but stretch your day an extra 2 hours and spend that extra 2 hours figuring out who needs to know this. Because I started talking about airborne EM in California in 2008. I went back, I got slides from Esben, and I just started talking. And then someone said, oh, you need to go to the top. So I talked to someone at the state, and they said, oh, you need to talk to the locals. So I went to all these groundwater agencies giving talk. So it's like, I really, personally, that's the message I want to get out there. If we want geophysics adopted, we have to be going to the people. I was just talking to someone from LA last week, Craig, and he was out with their engineering team putting in water pipe or something. They're working on this road, and he said there's about 30 different utilities on this road, and they've got their old PDF showing the layout, and they're spray painting. And he went, there must be a better way to do this. So he got in touch with a friend of a friend. He hadn't even got this far in his story. And I said, GPR. Sure enough, they bring GPR. This is LA. And this happened 3 years ago. How can they not know about GPR for this application? And the guy from LA said his field engineers were in tears of delight. The time savings, the accuracy. So we just need to be changing who we're talking to, or just walk into someone's office and don't leave until they'll listen to someone at the State Water Resources Control Board I met at a reception. He said to me, I finally drank the Kool-Aid. So.
And to add to that, Rosemary, I think you're right. That's what I've talked about with some others, and that is, if you need to get people in a number of areas that are also advocates. Right. And they're out there talking about it too, because they've seen it, they've seen the results from it, and they believe in it, because there's a lot of people who don't know about it, like we touched on at the beginning of the talk, the panel.
So I want to also kind of take all of this and tie it also into a question of, assuming all of this gets published and all the work that we're doing, what would it take for someone to do something like this, or for this type of method or similar to be effective outside of California, or in a
Mexico
area? Yeah, so New Mexico is exactly that's one example.
They're starting up. There's starting
so many places in the U.S., international, that need to do groundwater management, and so and this is both technical side, what's needed, and regulation side, and maybe Katherine can speak on that. What kind of regulations do we have in place now that you see other states could take California's lead on?
Yes, Katherine, you're up.
Yeah, well, I'd say certainly sustainable groundwater management, right? So I think in California, we were experiencing such exceptional drought that there was a cause and a need to push for sustainable groundwater management and to change the regulation. But that's really very difficult. It takes an extreme event like we had here, but the pushing also comes from the people, right? The other thing, the question about how we can get this, get this type of geophysics used in other states. I mean, at the state level, we are certainly having conversations with other states and sharing with them the work that we're doing, sharing them how geophysics is used, what we see in geophysics. So we have, showing them our data viewers. So it's really easy then for other non-expert users to access and use the data and see the benefits. And then they can talk to, their legislature as well, or they can talk to their management and say, hey, in Oregon, we just had this conversation with the state of Oregon, letting them know the data that we had, showing them the data that we had on the border, showing those hydrogeologists what type of information they could get about volcanics in their area. And, I expect that they'll go then talk to their managers will talk to their legislature, it's getting the word out. And I think really also in California with this statewide approach, it's gotten quite a bit of traction. And so we do have some statewide or some high-level cheerleaders of geophysics. And so I'll hear, the director of the Department of Water Resources talk about the statewide AEM surveys and the data that it provided, or also, the secretary for the California Natural Resource Agency talking about the data. So, it's the word, it's getting out there and they're sharing this information with the other states. So I think it's word of mouth, showing that the data is useful, showing users the data is useful, and then having other high-level folks talk to each other and say, hey, these are useful data sets that can help us in what's now becoming a groundwater management problem across many places in the state and many places in the country, as Craig, you showed that a lot of states in the West now are having drought issues. So it's yeah.
And I'd just like to reiterate that a little bit. Like last week, I was just at the Colorado River Forum and spoke with assembly members for like all the 7 states compact, and it was the same sort of thing. We showed them some of these types of data sets, what they can do, and how there's, they could benefit and use that to make, science-based decisions. And we heard about all the problems in their states, different watersheds, but we told them what we're learning here and these pilot projects everywhere in different states that we're doing, like upper mountainous watersheds down to California doing airborne EM and stuff like that. We said, you can learn from this and replicate it. Everything we're doing is transferable to your states, to your watersheds, et cetera. So these are, that's how we get it out, right? We just find those advocates and we keep continuing to showcase the success of these pilot studies.
Kevin, you raise your hand.
Yeah, so I'm still it's been recent enough time that I've been a student that I think one of my questions that comes to mind is, if you were an undergraduate or a grad student or a recent graduate or a geophysicist who wants to get more involved in this kind of work, or maybe pivot their career towards helping more efficient management of groundwater resources from the geophysics side, do any of you panelists have suggestions or thoughts on what the career market and the opportunities might look like now and perhaps in the near future?
Oh, I can say I have consulting firms approaching me that can't hire enough geophysicists. So, I mean, in California right now, there's a lot of people recognizing the value of geophysics. And yeah, and there soon will be in other states. So, yeah, so I am very encouraging of students to consider geophysics. I've got 3 more geophysics major recruits just for my course this quarter.
All right, excellent, excellent.
Rosemary, did you have anything else you wanted to say?
I had a quick, Craig. So the idea that this is transferable, I'm always very cautious. I've had people say to me, can you just bring to wherever? everything that's being done in California. I mean, we took the SkyTem technology that is being flown around the world, but before we could let it loose in California, it literally took 2 years of pilot studies thinking through the optimal workflow. Because, yeah, so I always tell people there will be at least a year of pilot studies and rethinking the optimal way. What's the optimal way to acquire data? Do you really want to use the SkyTem system, or do you want to use a fixed wing shallow imaging? So even though at a high level, completely transferable, that's a great message. But wait, don't just grab what we did here and apply it. Like in Denmark, it rains, the water table's at the ground surface. They had never had to grapple with the idea that you need a different transform, resistivity to sediment type, in the Vado zone, which can be 100 meters thick in California. So anyways, just a cautionary note there.
Right, and I'll kind of follow up with that is, and yes, I had thought about that too, and that's why I advocated at at that meeting that they should go for, because a lot of the assembly members wanted to know, well, what can we do to get the federal government to help us solve this problem? Because this was all about Colorado River water, imported water, and lack of water issues. And I said, well, advocate to the federal government to have funds that get you in touch with and can have geophysicists, experts in the field, be in touch with the states and make these plans, right? And have a plan. So I think that's what I advocated for, not on my own behalf, but on everybody's behalf. That that's where we need to go.
It does take a demonstration project. Like I was starting to feel like no one believed that Maxwell's equations were valid in California. And so teamed up with AGF and acquired that data set in Tulare that just everyone went, oh my God. So someone does just have to step up to the plate, drain their gift account, and go do it.
So what's next for California for this project? You or Katherine or both could apply. What are the next steps? What are you doing? I mean, all this airborne data has been collected already, right? And so, are there other data sets to be collected, or is there other geophysics to do? And what are the goals going forward?
Katherine, you want to talk about the AEM, and I'll talk about the other stuff.
Sure. Yeah. So as I mentioned in my presentation, we're really focusing on how to use the AEM, and as Seogi, you mentioned, other data sets, right? So not the AEM alone, but how to integrate the AEM with other data sets together to create these 3D maps and models that become decision support tools, right? So then to make the geophysics, to take it from that geophysics space to a real local groundwater manager usable space. So that's what our basin characterization program is focusing on. So that's in terms of using that airborne electromagnetic data. We may go back and collect some infill data if there's a need for it. What we're finding now is that we're using the AEM to do enough of this aquifer recharge potential mapping at this point to then go in and support locals by collecting this higher resolution towed EM data. So that's really now what we're focusing on. Actually, we're right now in the Fresno area in the central part of California collecting towed electromagnetic data. So that's our next steps. And the other one that I mentioned is also this interconnected surface water component that is really something that's difficult to understand. And that's, again, how surface water, so how rivers are depleted due to the pumping of groundwater. Mm-hmm. And so the next step that we're also doing is going to be collecting this flow TEM data, this data collected behind the boat along several river segments in California to help better understand what the structure is beneath those river systems, to get that information into a groundwater flow model so that modelers have a higher resolution understanding of what the effects are of pumping here on that surface water river system. So we're focused on using the AEM data, developing tools, making those tools publicly available for folks to use, the AEM data that we've already collected, and then now going in and collecting higher resolution surface-based data.
Okay, thanks.
Yeah.
So, and what we're doing, I'll put the link in the chat. So we've just started a 5-year project with 10 Stanford faculty involved, about 30 people outside. Craig, that's what I'm trying to email you about, called Taking the Pulse of the Watershed. And so it's the idea of how do you start with your airborne EM data that gives you the large scale structure of your groundwater basin and use other forms of satellite data, sensors, to adaptively manage our freshwater systems towards sustainability, really paying attention to the needs of ecosystems. So using satellite data to monitor when we have stressed ecosystems because surface water is being depleted. So mapping, measuring, monitoring everything we can. And I'm most excited about working with the groups that are building these low-cost sensors. So stream gauges, if we start trying to understand interconnected surface water, groundwater, it'd be much easier to do if we didn't just have, I think we've only got like 12 stream gauges in the San Joaquin Valley, and a stream gauge costs $15,000, and the USGS tells me it's $150,000 a year to maintain it. So there's someone now in electrical engineering here building a LiDAR-based stream gauge that doesn't sit in the stream where it gets blown out every time it floods, but sits along the bank. And he's telling me once commercialized, the price would drop to $500. So I am most excited now, not with the geophysical technologies, but the other technologies, the ancillary data we need to really fine tune and improve our interpretations. How can we build these low-cost sensors that we can deploy? How can we get cheap soil moisture that we can deploy everywhere so we can downscale the GRACE data set? How can we use seismometers and ambient noise to estimate what? So I put the link, the proposals there. There's an ongoing seminar. And no, I'm really excited now about the everything else. Go, Craig.
All right.
Craig?
Yeah, I just want to add to what Rosemary just said, and I was going to mention it to Katherine too, and that is, these Internet of Things, right? I kind of pointed to that in that one slide of technologies, and Rosemary, happy to share with you some of the stuff that's coming out of the stormwater like the stormwater industry, because there you have a lot of flow in pipes, and it's really hazardous conditions, and there's some really cheap, maybe a couple $100, 3D printed radar velocity sensors that I'm installing inside dry wells to monitor the flow coming out of pipes, because you don't have a weir or something to quantify that. So, or maybe, Katherine, even using like the distributed temperature probes, these sort of things that can go in, they can relay back already real time what their temperature data is in real time. And you could use like the diurnal heat flux as just estimating recharge like inside the river, right? And then couple that with your stream to understand whether or not it's losing or gaining at different times, really to quantify. And yeah, the Internet of Things is really exciting. I find it exciting too. It's really cool.
And the low-cost telemetry that we're getting now,
Yeah.
It's amazing. The advancements in sensor technology over the last, I would say even in 5 years, it's just continuing to take off. Low cost, low power.
Yeah. And so Seogi, now it's on you, man. Now it's on you to do the AI big data set, because we'll have more data than we can handle.
What's the results?
I have a quick question.
So we're building a digital twin. I think I'll call it a digital Seogi.
Yeah, that
Twin's
sounds
name
good.
is Seogi.
I like that better.
I have a question for Katherine. So, the statewide airborne EM survey, the logistics, I think it seems like an easier for the local scale. Like now you're working on a much smaller scale. You cannot cover all of them. So how kind of that sort of, because probably everybody wants their land to be surveyed, and maybe not, but then, so how are you prioritizing those local scale survey, and then how are you communicating with the locals?
Yeah, it's I mean, I don't know if you guys know, but it is sometimes more difficult to help folks for free than you expect, right? So it is quite a bit of work actually to go in and to collect data for folks and help them. So we do have a series of local groundwater investigations, is what we call that, underway, in which we first connect with the Groundwater Sustainability Agency. So again, we have strong connections with the groundwater managers. And then from the groundwater managers, that's our connection to locals. So in the Fresno area, for example, right now we're collecting data in Fresno Irrigation District detention basins that are already going to be built. And so we're helping them better understand what that engineering should be on those basins that will be constructed, right? Will it be slower recharge? To your point, Craig, about mapping those recharge facilities. If it's slower recharge in an area, maybe you want to do some additional infrastructure, engineering infrastructure to get water down more quickly, because these are basins that are already purchased, right? And then in other areas, so the north of Fresno, we're working with Madera, where we're working directly with growers, and we're collecting so the Madera, actually, Groundwater Sustainability Agency, did the work of asking their local landowners, do you want to conduct recharge on your parcels? So then we had that information. We had these aquifer recharge potential maps that showed which parcels had higher potential. And then we could work with and target those parcel owners to say, are you interested in conducting these, in conducting totem surveys to better understand what the recharge potential would be beneath your parcel? And so that's another, that was an easy connection there. We're also working in the Sacramento Valley, doing the same type of work. Again, always working first with the Groundwater Sustainability Agency and then having them connect us to the locals. But to be quite honest, it is difficult, one, to get locals interested. That takes quite a bit of work. And then also, to get boots on the ground to collect data, because we are a state agency. There's a lot of license agreements that you have to go through. You can't collect data everywhere. So for example, there are a lot of environmental concerns that maybe we don't think about normally when you think about going out to collect data. But the environmental concerns can be quite significant. So then other methods like drone-based methods where you don't have to put feet on the ground become quite appealing. There's a lot more coordination to do. And in fact, this is why it's taken us almost 6 months to a year to start these land-based geophysical surveys. But now we're getting into a groove, and we're going to conduct these surveys here in the fall, and then additional surveys up in the Sacramento Valley area in the spring. But it's a lot of coordination.
Okay, great.
So, actually, I have a question. So this is Seogi, you mentioned this earlier when you were discussing interpretation of results and crafting models and things. And some of the commenters also mentioned it, in that our models are inherently subject to a certain amount of uncertainty, right? And so as geophysicists, we've gotten used to a certain level of uncertainty and being comfortable with this in our results. But how does this, in your experience and panel in general, especially those of you who are working with clients or the public, how do you communicate to people about this uncertainty in your results? Because the thing that sinks geophysics quicker than anything else is we tell them one thing and it turns out to be wrong or not exactly what we've told them. And then they say, oh, well, this is hogwash. So how do we communicate the fact that what we're giving is our best guess of what's there, I guess? And what kind of experiences have you all had with this?
Catherine's nodding, so let me hear some words.
Oh yeah, I'm just going to say that communicating uncertainty is one of the most difficult things that we do, right? So uncertainty, I think, to understand in a quantitative way is difficult. And so when you are trying to make things as simple as possible to communicate to a local groundwater agency or a grower, it's very difficult. So I think we have multiple times, and anytime we start working with a new consultant, we ask them to help support us in communicating uncertainty to groundwater sustainability agencies, but it's very difficult. And so the best that we can do is to be transparent with everything that we do, right? So we say, we have provided an interpretation of the airborne electromagnetic data. We have the data always available if someone wants to reinterpret it or re-examine it, right? But this is just an interpretation that we have and one of the results. But it's a very difficult topic to communicate to the public.
Okay, Craig, you've got your hand raised.
You're muted.
Okay, yeah, Craig is.
Oh yeah, sorry about that. Yeah, I'll just kind of reiterate, and this was a big topic of discussion on a workshop that Seogi and I were part of. Was just uncertainty in groundwater, right? And that's not only the modeling, right, from the experts that are doing modeling and from the consultants, but then also like for us who are providing data to them. And so you have uncertainty going into a model and it produces more uncertainty. So this is a topic that we have said really needs some work on in the next coming like 5 to 10 years, right? That we really need to address uncertainty and how we convey it, but also how we deal with it in our models and how it's passed through. So yeah, not an answer. I'm not giving you a solution. I'm just telling you we've recognized it.
No, and I have to say that when I was presenting the groundwater architecture project at the Groundwater Resources Association meeting to hydrologists and water managers, and I planned to talk about uncertainty because Seogi'd been producing some, sediment type interpretations, but shaded to say if it's dark, I'm very confident it's sand and gravel. If it's transparent, I have a lower level. So doing that. And a fellow geophysicist at a consulting firm said, do not talk about uncertainty. If you talk about uncertainty, no one will ever use geophysics again. I talked about uncertainty. And after the meeting, people came up to me and said, thank you. Now we trust geophysics. We never believed that given all the unknowns that you're solving for, you could possibly be as certain as we're led to believe at times. And so I just think we're doing ourselves a disservice by not declaring uncertainty. So I appreciate the efforts Katherine and team are going through to make it clear to everyone that there is uncertainty. And my preference of the way you talk about uncertainty is you say, what are these data being used for? And you show the uncertainty in whatever it is they're trying to predict that's due to all the, anyways.
And someone mentioned groundwater flow models, and I just want to mention that there is so much uncertainty, right, in the data that we are creating, and that then goes into a groundwater flow model. You don't hear groundwater flow modelers talk about all the uncertainty in their data sets and in their interpretations. But let's be clear, there's a lot of uncertainty there, but we're all just, I think, trying to get the most information that we can out of a data set and try to produce a useful result. And so in our program, at least, we know that, is it necessarily the best result today? Can it be improved? Can we reduce uncertainty? Can we make it better by integrating more data to reduce uncertainty by a different processing and interpretation approach? Yes, right. And we'll do that in the future, but we can't let that perfection and that reducing uncertainty to nothing not stop us from getting something out that could be useful to a groundwater manager today.
Oh, I would never advocate reducing uncertainty to nothing, but I think it's like declare that it's there at least. Yeah.
And Rosemary, what you said is exactly the point. You really need to have open discussions with your stakeholders to understand what their needs are and what they're trying to solve, because then that helps you talk about uncertainty. Right. That's the most important thing.
Okay. All right. Well, we've been at this for about an hour and 45 minutes. I thank everybody for this.
I want to thank you guys for doing this, getting us all organized.
Part of the process. I appreciate my own efforts because I learned a lot during this meeting. Then it'll be a challenge for me to now condense this into a 4 or 5 page article in the Leading Edge. And remember to look in your mailbox or try to get a copy of it on March 2026, and it should be a great issue. Thanks everybody again for participating. And any last questions? Speak now or forever hold.
Any closing comments from our panelists? What you're up to next? Stuff you're excited about?
I think that was already fairly well covered, but
I just want to mention one more thing so at the department we have created a network and meeting series to get information out to other consultants or academia who are working on basin characterization type issues, who are using geophysics or groundwater modeling to characterize basins. That meeting series is called the Basin Characterization Exchange. And I would encourage folks, if you're interested in attending this monthly series, we have a lot of interesting speakers come out. We had Graham Fogg speaking last month. And next month we'll have some talks on environmental sequence stratigraphy and integrating data sets into that. So it's really just about what are the data sets that we can combine together to characterize our groundwater basin. So if you're interested in that topic, I would encourage you to tune into one of our basin characterization exchange meetings.
Great.
Thanks for just letting me add that in real quick.
Could you give us a link to that, or is it, and then we'll do that.
Yeah,
we'll
just drop it in the chat. We'll
drop it in the chat. I think we will be able to capture the chat. So again, thanks everybody else for coming. This has been a great experience. I really enjoyed this. And for that, I will close this meeting. We'll try to.
Thanks, everybody. Thanks for having us.
Thank you.